Gravitation Part 2. As always, if you enjoy this content, give us a like and subscribe. So, we have talked about this idea, and now we're going to do a derivation to finally deal with it. So, the concept is this. If we want to find the velocity or the height or anything for an object that's thrown from the surface of the Earth or any planet up into the air and then it comes back down, the general issue or problem that we've dealt with here goes away because R2 and R1 are essentially the same. So this change in height doesn't have a large change in gravity. Yes, the further we get away, G goes down, but because the change in height of R2 minus R1 is so small, the change in gravity is essentially zero, and we can use change in PEG for our change in potential energy because the height being so small means a small change in gravitation. So this formula is actually an approximation. So how do we figure out a formula that deals with this change in gravity? So the way that we're going to do this is we're going to do an integration. And the reason that we're going to do an integration is because if we take a small mass right here, this is some small mass, and we move it so that it's changing its potential energy as it's moving between this changing gravitational field, the force is going to change. And this distance, which we're going to call r at any position, is going to change. And so we're going to call the surface of the Earth r, but then we're going to be able to look at this for different r's all the way out to infinity. So we know that if we're moving it, let's say we're moving it from infinity back to r, that distance, as we move it back, is going to be in the same direction as the force. And we know that that integration is the formula for work, which is the integral of f of x dx. And we're going to be moving it from infinity back to r, so that we can find that potential energy. So that potential energy is going to be from infinity to r, but what's that force? Well, that force is changing, and we know that that force at any instant in time is gm1 m2 over r squared, and we're doing this for our dx, which in this case is going to be r, so this becomes dr. Now, we can pull out the constants, which are going to be g, m1, m2, and we're left with the integral from infinity to r, r squared dr. And we know that the integral of 1 over r squared is equal to minus 1 over r. So that becomes u is equal to minus g m1 m2 over r from infinity to r. So now let's do our final minus initial. So our final is r, so that's minus g m1 m2 of our value r minus a minus g m1 m2 over infinity, which is going to be 0. So our potential energy at any value r is going to be u equals minus g m1 m2 over r. So that's our formula. And if you think about it, when we get out to infinity, this value becomes 0. So at infinity, the potential energy, u, is equal to 0 joules. Now that sounds like it has no energy, but think about it at some radius r from the center of the Earth, either the surface or some other point, then that becomes negative g m1 m2 over r, which is less energy. So that means the maximum potential energy is 0, which is a weird concept. But if you think about it, we've done this before when we got to choose the position of an object with potential energy. So if we decided to call this to be 0, then the potential energy of this point would be negative something. I don't know, negative 10 joules. So the maximum value would be 0. So let's go ahead and do a graph to sort of get a better handle on what's happening here. So we're going to say from 0 down to negative g m1 m2 over r. So that's at the surface of the Earth. And this is going to be our value at infinity. So our graph is going to look like this. As this approaches infinity, this approaches 0. And if we were to look at this for MGH, MGH actually is the linear tangent of this. So MGH is true, but as it leaves, this is where MGH stops being effective. It's effective down here when the slope of the line is very close to the negative g m1 m2 over r graph. So if we found this at any point r, this would be u equals negative g m of the planet, in this case Earth, times the little mass over r, and that r would be the position of whatever we decided to find it at. So when we're at this point, we would say u is equal to minus g m1 m2 over r, m1 being the mass of the Earth, m2 being the little mass there, we could call that 2. And at that point, that's approximately equal to negative mgh, where h would be the radius of the Earth. Escape velocity is the idea that if we launch a projectile off of the surface of a planet, there's some minimum speed at which the ball, or whatever the object is, a bullet or a cannonball or something like that, would leave the surface of the planet and not fall back down, but go so fast that the gravitational field gets so weak that it actually makes it to infinity. In other words, it's the speed at which it won't fall back down. So we know that at small speeds, it's just going to loop back and then here, and the faster we go, the further out it's going to go. But eventually we can get it out to the point where we're at infinity, where the gravitational field is so small, it's effectively 0. Now, one other thing that's important that sometimes comes up is that the angle that we shoot it at doesn't actually matter from the surface of the Earth, because the kinetic energy that it starts with is a scalar. So what are we dealing with in the beginning? Well, we start out with kinetic energy. So we're going to do this as a conservation of energy problem. So what is that? That's just 1/2 mv escape velocity, that's what we're solving for, squared. And we know that the potential energy from our derivation we just did is some large negative value, which is m1 m2 over r. Now, that's the total energy right here at the surface. And when we get out to infinity, what's our kinetic energy going to be? Well, the escape velocity is going to occur when the kinetic energy is 0. In other words, when the object stops and won't fall back down. And our potential energy here is going to be negative g m1 m2 over r, which is infinity. So that also is going to be 0. So we have 0 energy out here, and we have our combined energy here. So how do we solve this? Well, we can just do a conservation of energy. So we can say the sum of the energy initial equals the sum of the energy final. And we start with U gravitational initial, plus kinetic energy initial is equal to potential energy gravitational final plus kinetic energy final. So that gives us negative g m1 m2 over r of the Earth plus 1/2 m2 v2, which actually, rather than call that v2, let's call that v escape. squared is equal to 0 plus 0. And if we rearrange this, we can take this, bring it over to the other side. Our m2's will end up canceling, and we'll be left with m1, which will be the mass of the planet. So our escape velocity becomes the square root of 2g, mass of the planet, I'm going to say Earth in this case, over the radius of the planet, in this case, the radius of Earth. So what type of questions might they ask? They might say, what happens if we double the mass of the planet or double the radius of the planet? How does that affect the escape velocity? Well, if we derive this formula, we can just see what happens. If we quadruple this, then that would double the escape velocity. Okay, circular orbits. Let's pick something simple. We'll just say find the time for the moon to orbit the Earth. And we could do this for any satellite. So anything that's orbiting something else. And the way that we're going to do that is we're going to start out with the Earth, and we're going to have the moon here, and it's going to go in a circle. Think about the forces involved. We have the force of the moon pulling on the Earth, Fg, and the force of the Earth pulling on the moon, which is going to be Fg. And this is a force pair. This is Newton's third law. For every force, there's an equal and opposite force. Well, let's do a net force equation on the moon. So that's going to be F net equals ma equals, well, what forces are acting on the moon? That's only going to be Fg. Now, this is a force that is perpendicular to the velocity, so this is a centripetal force. So we can rewrite this as m1v squared over r is equal to, and what's that force of gravity? Well, that's gm1 m2 over r squared. So if we cross out one of the r's, we can cross out one of the m's, that's the mass of the moon, and we're left with v squared equals g, and that's going to be m of the Earth divided by r, and we have to be careful here because what is r? Well, in AC equals v squared over r is the distance from the point at which it's rotating around. So this is the Earth-Moon distance, the distance between the Earth and the Moon. So we can do a little side derivation here and say that v, this is for the velocity of the object rotating, v is equal to x over t, so that's one lap around the Earth, and how far is that? Well, it's the circumference, so that's 2 pi r. And what do we call the time for one revolution? That's called the period. And so we end up squaring both sides with v squared equals 4 pi squared r squared over t squared. Now, why did we do this? Well, it's because we can take this and sub it in for v squared. So that gives us 4 pi squared r squared over t squared is equal to gm of the Earth over r, and just remember that that r is the Earth-Moon distance, and that's the same r we have here. So rearranging, cross-multiplying, we can solve for t squared, and that's equal to 4 pi squared r cubed over gm of the Earth. And then squaring both sides, we end up with t equals, we can pull the 2 pi out, r cubed over gme. Now notice that it's not mass dependent of the satellite. So I'm going to write here, satellite mass doesn't matter, doesn't affect this. Okay, one other thing that I want to point out is that this formula works for any satellite. So think about why this is important. We could do this for the whole solar system. So that means we have the mass of the Earth, which doesn't matter as the Earth orbits the sun, and then we could do this for Mercury, Venus, and so on. And the only thing that matters, since the mass doesn't matter, is the radius. So if we deal with a planet that was more massive, let's say we put Jupiter at the radius of the Earth, then the time to go around would still be 1 year or 365 days. Okay, let's go ahead and calculate the total energy of a satellite in a circular orbit. Well, we've already seen that we can figure out the velocity using x over t, and that gives us 2 pi r over the period t. And we saw before that the centripetal force, in this case the net force, MAC, is going to be equal to the force of gravity. And if this doesn't make sense, just go back to the previous derivation. And then that gives us our gm1, I'm just flipping it, over r squared is equal to our centripetal force mv squared over r. And then cross multiplying, we can solve for we can solve for v, so that the v of the satellite is equal to the square root of g, m of the planet, or it could be the sun, depending on what the object is rotating around, over the distance away. So again, this is a very important problem, or formula to be able to derive. This usually comes up as pieces of larger problems. Now to find the total energy, it's relatively simple. What type of energy does this object have as it rotates around a central object? Well, it has kinetic energy because it's moving, and it has a height that we're calling r, so that's our potential energy. So all we have to do is put in 1/2 mv squared plus a minus gm1 m2 over r. And we just derived the formula for v of the satellite. So we can rewrite that as our E total is equal to 1/2 m, our derived velocity, which is the square root of gm over r squared, minus gm1 m2 over r. So we square that, that's obviously gm over r. And we can rewrite that as E total is equal to 1/2, pull out the g, mass of the planet, and let's do this for the sun. So we have mass of the planet, and then the mass of the sun that it's orbiting around. R would be the planet to sun distance, minus g, mass of the planet, times mass of the sun over that sun-planet distance. And when we put those together, we end up with E total is equal to negative g, mass of the planet, mass of the sun, all over 2r. So we now know how to derive the formulas for velocity of a satellite and the period of the satellite. Now, I'm going to do this for planets rotating around the sun. Notice, first of all, that the mass of the planet is not in the formula. So it's only the mass of the thing that it's orbiting around. So in this case, it's the mass of the sun, mass of the sun. And we can look at some actual real numbers, and I did these in millions of kilometers, the period in years, and the velocity in miles per hour. So you can see that for Mercury at 58 million kilometers away, it takes 1/4 of a year for Mercury to go around the sun. And it's traveling at 107,088 miles per hour, so it's cruising. But notice the trend here. First of all, the mass of the planet doesn't make a difference. It's only dependent on the radius. And as we go up, as the planets get further from the sun, the time it takes to go around gets longer. And the velocity decreases. So this goes up and this goes down. As we move further and further away, we can see the trend continues. It takes 29.5 years for Saturn to go around the Sun once, and it's not traveling very fast. So what are these relationships here? So we know that T is equal to this formula, 2 pi square root of r cubed over g, m of the Sun. Well, if we square both sides of this equation, we end up with T squared equals 4 pi squared gms times r cubed. Well, r is our variable, r is our change. So these are all constants. 4 is a constant, pi is a constant, big G is a constant, and the mass of the Sun is a constant. So therefore, we can say that T squared is directly proportional to r cubed. So if we were to graph this, we would get a straight line. It's a linear, this relationship between these two. And what is the slope of the line? Well, the slope of the line is the constant. So the slope, which we're going to learn later, because we're going to do this one more time because it's so important with Kepler's laws, is GMS. So what are the takeaways here? That as the radius increases, the velocity goes down and the period goes up, and that it's mass independent. Even though most of the orbits of planets around the Sun are close to circles, they're not perfect circles, they are elliptical orbits. So when we deal with planets, or whether Pluto is a planet or not, when you start to get out to things like Pluto, you start to get highly eccentric, which means very elliptical orbits. And the eccentricity of an ellipse is always between 0 and 1. When you're at 0, this means that the two foci are very close together. So in an ellipse, you have two foci. In the case of the solar system, one of those foci is one of the foci, I guess is right, is the Sun, and the other point is just an imaginary point that we use mathematically to solve these problems. So when these two foci get close together, then you start to approach a circle. When it's at 0, it is a circle. When they start to approach 1, the ellipse becomes a parabola. So it's no longer an ellipse at 1. And then when it is greater than 1, it becomes a hyperbola. So let's look at a little picture of this. So here's an elliptical orbit. We have our Sun at one focus, and we have our imaginary focus over here. This is just a mathematical point. And then we have the center of the ellipse. So the focus to the center is one distance. We could also say the distance between foci, this distance right here from focus to focus. And then we have the distance to the edge of the ellipse, which is called the semi-major axis, or we can do the distance between the two edges, which is the major axis. So the formula is this. If we divide the focus, so center to center, by the semi-major axis, that's how we get E, the eccentricity. But because this divided by this distance is equal to the double distance of the double distance here, so between foci and from one side of the ellipse to the other side of the ellipse, that ratio is the same. So we can say that the eccentricity is equal to the focus to the center divided by the semi-major axis, or we could say the distance between foci divided by the major axis. So Kepler has three laws, and the first one is very straightforward. All it says is that all planets move in elliptical orbits, and the sun is at one of the foci. So we have one focus here and then our other mathematical point. And an ellipse is defined as the locus of points for which R1 and R2 are constant. So wherever the planet happens to be, that distance from these 2 points, that has to add up to the same number. Now, I want you to think about this. When this planet is here, it's very close to the sun. So its potential energy is relatively low, so its kinetic energy is very high. We're going to see in the next law, angular momentum remains the same, so therefore when it's close it has to be moving faster. So here it's got lots of kinetic energy and not much potential energy, and out here it has not much kinetic energy. It's not moving fast, but it's far away, so it has a larger r, so it has more potential energy. Because these 2 points are often compared, it's important to name them. So this point right here is called perihelion. Helios, we get helium from, that's the sun, and para is from the Greek near. So perihelion is when the planet is closest to the sun. And this point also has a name you should know, and that's called aphelion. And again, ap from the Greek apo means away, and helion, helios, helium gives us far from the sun. Okay, Kepler's second law says that if we take a line joining any planet to the sun, so we take a line, we go from the sun, we go out to this planet here, that it's going to sweep out an equal area in an equal amount of time. So if we take this planet and it swings over to here, that consumes a certain amount of time and sweeps out a certain area between these 2 lines. Well, if this time equals the time for another planet or the same planet to sweep out the area down here, then these areas have to be equal. Or the converse is true. If the areas are equal, then the times it swings out have to also be equal. And this is the result of the angular momentum being conserved. There are no net external torques on the system. So what does that mean? It means that the L initial has to be equal to the L final. So let's pick a point out here and think about R cross MV. Well, out here we have L, which has to be the same at every single point around here. That has a large R. So that's going to be crossed M, but it's far away, so it has lots of potential energy, not much kinetic, so therefore it has a small v. And over here, at this point, at perihelion, we have the same value of L, but at this point, our R is small, but because it has more kinetic energy, M cross a larger V, but the L's are the same. Finally, we have Kepler's third law, and we already did this because we derived, and if you need to go back, you can go back and look at this. We already derived 4 pi squared r cubed, gm in this case of the sun. And so what's the takeaway from this? The takeaway is that t squared, the period, is directly proportional to r cubed. And if we say that t squared is directly proportional to r cubed, we have these constants. So again, we've done this before, but this is what Kepler's third law is, what it says. And that constant c, that slope, is the 4 pi squared over gm of the sun. And that's what Kepler actually was able to do. What's the main idea? As the distance you go away from the sun increases, the time it takes, the orbital period, increases. Geosynchronous orbits. So if we look at the word geosynchronous, we have geo, which means Earth, and syn, which means same, and chronos, which means time. So what this is saying with the Latin or Greek, I'm not sure which, is Earth same time orbit. Well, what does that mean? Well, by definition, it's a satellite which orbits at the same rate of rotation as the planet, so always to be above the same point. And another way to say that is the angular velocity of the planet matches the angular velocity of the satellite. So what's happening? Well, what it's saying is that as the Earth rotates around, a point out here rotates along with the Earth so that it's always above the same point. This has to happen at the equator. So let's look at some different orbital paths that we could potentially have. We know that the further out we go, the slower we go. So if we're too close, the Earth is going to be rotating at some speed where it takes 24 hours to make one revolution. But if we're too close, this is going to go faster. So this is going too fast. But if we go too far away, now we know that the speed is much slower. So this is going to go around in 24 hours, and this is just going to creep along and fall behind that point. So this would be too slow. And if we get it right, there must be some point between too fast and too slow where it's almost as if we had a cable out here and then that ended up rotating along with the Earth. And why is this important? If you wanted to take your satellite and fixate it on a certain point, you could continue to monitor that area at the same time. So if we wanted to write this out, we would say that those angular velocities must be the same. Well, from v equals rho omega, we can say that omega is equal to v over r. Well, that ratio must stay the same. So we could say v at the equator over the radius of the Earth, so that's the angular velocity on the surface of the Earth, that must be equal to v of the satellite divided by the radius that the satellite is out there. So you can use this formula to figure out that geosynchronous orbit radius.
This is a visualization of the thousands of satellites orbiting planet Earth. Most of the satellites orbit just above the Earth's atmosphere. But I bet you're wondering at this ring. Why are so many satellites lined up in that circle? This is the geostationary orbit. Satellites at this height have an orbital period of 24 hours. Their angular velocity matches the rotational speed of the Earth, making them appear stationary with respect to planet Earth. This feature has a huge benefit for communication satellites. So where do we plant our satellites for them to be geostationary? It would be nice if satellites can orbit along the latitudes. But such orbits are not attainable. For circular motion, satellites need a net force that's directed towards the center of the circle. But the Earth can only pull the satellites towards the center of the Earth. That's why all satellites with circular orbits must be centered about the Earth's center. But any orbit which is inclined to the equatorial plane is obviously not geostationary. Such orbits bring them in and out of the two hemispheres. Of all the orbits in the equatorial plane, only one has an orbital period of 24 hours. A satellite is falling around the Earth at a rate decided by the gravitational field strength. The further away from the Earth, the weaker the field strength, the slower the satellites fall around the Earth, and the longer the orbital period. For an orbital period of 24 hours, we have to bring the satellite to 35,786 kilometers above the Earth's equator. It's a long way out, but it's worth it if you want to be geostationary.
Finally, we get to transfer orbits. So we're going to pick a point like here, and we'll say that that's the Earth. And we have a spaceship that is out here, and like the space shuttle or something like that, and it's in a circular orbit. So if it's in a circular orbit, you don't need to do anything to keep it in a circular orbit. You have a constant force that's giving it a centripetal acceleration. But what if you want to move it into a larger orbit? Well, if it's moving in this direction and you apply a thrust to it so that the thrusters are going out like that and you end up experiencing a thrust in this direction, then what's going to happen is it's going to speed this up and move this out into an elliptical orbit. Now, we're not talking about a constant thrust. We're just saying it's going to give a burst. So it gives this burst, which speeds up its velocity, which makes it spin out to a much larger orbit. Now, the problem is you may not want to stay at that orbit. You want a new circular orbit further away from the Earth. So what you then have to do is apply a second thrust out here that matches the velocity that's necessary to be able to keep it in this orbit.
Welcome to this Lab Rat Digital Lab. Today we want to talk about how to transfer from one orbit around the Earth to another higher orbit to make a rendezvous with something like the space station. To do this, we'll use the Hohmann minimum energy transfer orbit. Okay, so what do I mean by a transfer trajectory? First of all, here's my simple circular orbit around the Earth. This is my original orbit that I start off in. But what I ultimately want to do is achieve a higher orbit to rendezvous with a space station. Now to do that, I need to go from the lower orbit to the higher orbit, and I use an elliptical transfer orbit. Now the Hohmann transfer is a minimum energy transfer, which means I need the least amount of delta V, the change in velocity, to get me to move to the higher orbit. Here's my spacecraft, and the first thing I need to do is fire rocket motors to change the delta V of the vehicle to pick up the new elliptical transfer trajectory. So I only fire my rocket motors for a brief period of time and then coast most of the way to apogee of the transfer ellipse. Now, if I don't do anything at this point, the spacecraft will continue to follow along the elliptical orbit, and I will not achieve the desired circular orbit at the higher altitude. Let's try this transfer again. Now this time, I only want to use half of the transfer orbit because I want to fire my rocket motors at apogee to achieve the new desired circular orbit at the higher altitude. So once again, I fire my rocket motors to enter into the transfer ellipse. Now I only burn my rocket motors for a short period of time and again coast until apogee. Now once at apogee of the transfer ellipse, I need to reorient my spacecraft and fire my rocket motors once again to add delta V to the trajectory to circularize the orbit at the desired altitude. Once I do that, my engines cut off and I coast and remain in the new higher circular orbit. Now, as I said earlier, the Hohmann transfer is a minimum energy transfer, which requires the least amount of delta V, but it also takes the most time to get from the inner orbit to the outer orbit. Now, it is possible to have a faster transfer orbit, but that means I'm going to have to add more delta V at the lower orbit and then have a higher delta V in order to change the velocity to achieve the new higher circular orbit. And that's depicted in the figure at the right. Now this requires more delta V, which requires more propellant, which makes the rocket heavier and more expensive. So ideally, we like to use the Hohmann transfer to do things as efficiently as possible. Okay, that will do it for this digital laboratory. Make sure you go to labratscientific.com for more detailed information on this subject.